As I believe you will discuss today, the success of computational modeling challenges some conventional thinking about the nature and functions of modeling itself. In all of his accomplishments reflect the highest standards of clarity, precision, elegance, and beauty. In Shakespeare's words, they look into the beauty of thy mind, and that in guess they measure by thy deeds. Now, as the Old Testament reminds me, it's a foolish thing to make a long prologue and be short in the story itself. So let's welcome Jack McDowell and listen to his story.
Well, thank you so much for that, Jack. Very nice introduction. I was going to bring the book today. I was going to bring the Wolfram book today, but it's gigantic. You probably can't tell that from the image, but the form factor is enormous and it weighs 6 pounds, so it was very hard for me to bring it. Some other features about this book: it's 1,300 pages long. It's huge. About a third of those pages are small print footnotes, which, by the way, that's a lot of that is some of the best part of the book, the footnotes. There are 600,000 words in this book, approximately. Half of them divided, half of them in the main text and half in the footnotes. And there are 1,000 illustrations in this book. It is huge, and it's badly it needs an editor. Wolfram self-published this book, published by Wolfram Media, and of course didn't have to have an editor, and he could use one. But nevertheless, and this book has been criticized for lots of different things, but nevertheless, I think it's an interesting book and has a lot of interesting things that could be of value to behavior analysts. Oh, by the way, the summary of the whole book you see on the right there. All the wonders of our universe can be captured by simple rules, which I think is the last sentence of the book or close to it. Now, how do I... here you see, these images that you see are time-evolved images of one-dimensional, two-state, nearest neighbor, cellular automata. That's what these are. These are the bread and butter of Stephen Wolfram. These are the things that he likes best. These were invented by John von Neumann, but Wolfram made, and others have made a study of these, and these form a very significant part of this book. On the left, you see a pattern that is referred to by Wolfram as chaos. And I want to describe to you just briefly what these cellular automata are, and I'm going to go in more detail, talk in more detail about them later. You can't see in these images, but in fact, because I'm very zoomed out, but if you zoom in on these images, you'll see a bunch of squares. If you think of the very first line of the image on the left, it's a line of squares that can have two states. So the single line, that's the one dimension. Each square can have two states, 0 or 1, white or black. That's the two state. And the lines progress down the page as time goes by. And obviously, the decision that needs to be made is, if you're a cell in the first row with a particular state, what should your state be in the next row? Well, that's determined by your nearest neighbors in the simplest cellular automata, as this is. And so that's why that's the nearest neighbor part. So, for example, if I'm a white cell, I could have two white cells as neighbors, two black cells, a white cell and a black cell, or a black cell and a white cell. There are 4 neighbor conditions if I'm a white cell. If I'm a black cell, there are also 4 neighbor conditions that I can list. So I can list the operation of the cellular automaton in a table consisting of 8 lines. There are 8 neighbor conditions, and given the neighbor condition, that's going to determine what state I am in the next generation, or the next line of the cell. So I can assign for a particular neighbor condition either a 0 or a 1, a white or a black for that. So because there are 2 possible states that I can assign to the 8 neighbor conditions, I have 2 to the 8th, or 256 possible cellular automata. And that's basically how these devices work. Now, what you see on the left are, there are 2 important things about a cellular automaton. One, you have to have initial conditions. And the initial conditions can affect how the automaton works. Secondly, you have this table with 8 lines in it that completely specifies the operation of the automaton. Once you run these, you see things like you're seeing here. Structures emerge in the operation of the cellular automata. And here on the left you see a lot of triangles. There are different sizes. There's some gullies. I don't know if you can see the gullies. There are some gullies there. And what Wolfram means by chaos is really just highly irregular. It's highly irregular. If you have looked at that pattern of triangles and have attempted to see any repetitions, you couldn't see any. You couldn't find any. There are no patterns like, there seem to be little groupings of small triangles here, but you're not going to find exactly that same thing anywhere else. This is about 300 steps in the evolution of a cellular automaton. So that's an interesting result, but not the most interesting. I don't have a uniformity example up here, but I'll give it to you. It's not the most interesting result. The most interesting result is over on the other side. This is a cellular automata that works exactly the same way, except it has a different table that specifies how it operates. And what you see in this automaton is also the emergence. That's an important property of these, the emergent structures. The emergence of complicated structures that take on characteristic shapes and that move through time. Remember, the time progresses as you go down the page. So, for example, you see this structure, which is two black lines. Well, the first thing you see is like the Big Bang. There's debris that occurs here, and then particles, you say, or structures condense from the explosion. So you see this little structure turns into this one. This descending pattern of triangles is a very important feature of this particular cellular automaton. These all have names, by the way, all of the different structures that you see in this one. And you see this structure elsewhere, like you see it down here, the same structure. You see these various curlicue structures here repeated. So you see these structures emerge and move through time, and you also see them interact, interestingly. It's like particle interactions. So you see this curlicue structure, for example, and this other linear kind of structure coming in from the right. They crash and turn into these other two structures, which then continue in time. This outcome, and this automaton is specified, we're going to look at it in a little bit more detail later, is specified with just an 8-line table, just like any other is. This outcome is referred to as complexity, and this is the central focus of Wolfram's book. That simple rules, as are specified by these cellular automata, can produce complicated and interesting structures. Whoops, I went backwards. Okay, so let's look at that, and that's what this new kind of science is. Now, we know that complexity theory has been around long before Wolfram, but Wolfram really secluded himself for about 10 years in order to study these things, and I think sort of got out of touch, or he doesn't particularly like to refer to in great detail to earlier work, and that has caused some criticism also. So there's been complexity theory around before Wolfram, and the Santa Fe Institute is a great example of that. But Wolfram is an extreme practitioner of complexity theory, that simple rules can generate complex phenomena. So if we see complicated phenomena out there in the natural world, like the behavior of organisms, it might be that simple rules underlie those phenomena, and that in order to understand them or describe them, we need to know what those simple rules are. And those complex phenomena then would be emergent properties of the rules, just like the structures in the cellular automata are emergent properties of the simple table of 8 neighbor conditions. A very interesting feature of this perspective is that it is necessary to abandon traditional, continuous analytic mathematics, because although differential equation-based mathematics has been very useful to science for a very long time, according to Wolfram, this new way of looking at things, you've got to talk about the rules. So you need to specify the rules to have a theory, and the only way you can do that is in a computer program. So you program the rules in your software, and you make the rules operate, and then you look at the outcome of your theory. So these computational theories then may describe the natural world. So that's a summary of the new kind of science that Wolfram would like to talk about here. Now, when I talk about mining Wolfram, one vein of material to mine are these computational machines that he talks about. And there are many more besides these simple cellular automata. They can get much more complicated and do get much more complicated. There are a lot of very interesting sets of rules that are worth looking at, which might apply or might be of use to us in behavior analysis. But there's another vein, I think, that's really interesting in this book, and that is a kind of it's a number theoretic vein. I say number mysticism. I put Pythagoras up here because we know that, although we don't know that much about Pythagoras, the Pythagoreans were number mystics and thought that numbers really had a special relationship to the natural world, and this was an influential point of view, as we know, in later science. And so when I'm reading this book, I have in the margins, I keep writing Pythagoras, because he has this kind of appreciation for number, or this number theory is such an interesting vibe that goes through this book. That's another thing that is actually very exciting. And a lot of the footnotes talk about number theory and educate us about number theory that we don't know about, that's really very fascinating. And I'm going to talk about a few of those things. So I recommend Chapter 4 in that book and the footnotes on Chapter 4, which talk about number theory extensively. So let's look at these cellular automata. I have here one of these tables, and here are the 8 lines in the table. 1, 2, 3, 4, 5, 6, 7, 8. And here is the cell that I'm talking about, and here are the 2 neighbors. These are the 8 neighbor conditions for this cell. It can either be white cell or black cell, and it can have these different conditions. So you see, this is a white cell that has 2 white neighbors. This is a white cell that has a white and a black neighbor. And this is the outcome. This is what the cell is going to be in the next step. So this cell with 2 white neighbors is going to be white. This cell with the white and a black neighbor is going to be black, and so on. Notice that these are binary representations of the first 7 decimal integers. 0, 0, 0, 0, 0, 1, 2. This is 2 to the 0th, 2 to the first, 2 squared, 2, 3, 4, 5, 6, and 7. So you don't have to in order to understand how these operate or work with them, you don't have to remember anything. You just write out the first 0 through 7 in binary representation, and you have the condition table on the left. And then the table on the column on the right specifies what the next outcome is, what the outcome is. And this just is one outcome that you might be interested in. If you pull these numbers down and look at them as a bit string and ask what their binary, what they represent, what's the decimal integer that they represent, that decimal integer is the name of the rule. So that's where so this is called Rule 22. So all you need to know about a cellular automaton, and this is the way that people talk about them, is it's Rule 22, it's Rule 150, it's Rule 105. You know already what the condition table is going to be. You can just write that down. And then you can write down the outcome column just from knowing what the name of the rule is. You just write it out in binary and pull it up into that column there. This is another way to specify cellular automata, and Wolfram loves this. He's very visual. This is 000, 001, 010. So 0 is white and 1 is black. That's the condition table, and that's the outcome column. That's just a different way to specify them. Let's look at uniformity. This is Rule 22, which we just saw. And here, the initial condition is a single black cell. At the top, you can sort of see that little black cell, but it's still pretty tiny. And then you just turn on the cellular automaton, follow the rules, and it produces this, which is sometimes called a Sierpinski gasket. You've probably seen this before. It has fractal structure. It repeats itself and is self-similar. And it is interesting for a number of reasons, but not the most interesting thing as far as Wolfram is concerned. There are a lot of ways to produce a Sierpinski gasket, not just this way, but this is one rule that produces them. Here's Rule 22 with a different set of initial conditions. It has 2 black cells surrounded by 2 white, surrounded by 2 black. Way up here, they're very tiny, you can't see them. Turn on Rule 22 and make it work, and here you get a different kind of chaotic outcome. Now I've extended it to 300. It continues up here. 600, it continues up here to like 900 generations, something like 900 generations. It has mirror symmetry down the midline. However, if you look down the midline, again, you don't see any repetitions of structures in this outcome. So, for example, here is this strange larger triangle made by smaller triangles with a little curvy top, but you don't see that anywhere else. Here's a kind of rocket engine, looks like a rocket engine, a triangle with 3 smaller and 3 even smaller triangles, but you don't see that exact thing anywhere else here. So there's a chaotic outcome in a cellular automaton. These also can carry out computations, interestingly, essentially any computation. Here's Rule 132, and there's the specification of the rule there. Rule 132 can identify, based on initial conditions, whether a number is even or odd. So if the initial condition consists of the number of the black cells equal to the number that you're inputting, you could say, this one, for example, 3, and then you turn on the cellular automaton, if the number is odd, it will end with an infinite black line down here. An even number will end with a pair of white lines that continue forever. So this cellular automaton carries out that computation, just an illustration that these devices can do computations. Here's another one, a little more complicated. Rule 152 carries out this computation, which essentially is dividing an even number by 2. If it's an odd number, it will divide by 2, take the integer portion, and add 1. But let's just consider an even number. The initial condition, the even number, is specified by the number of black cells. In this case, I've really exploded the grid, so now you can see all the cells. But here you see 6 black cells, and here are 10 black cells. Turn on the cellular automaton, just follow the rules, and it produces in its final, it settles down to producing a string of black diagonals that continue then on forever. And you can see this one produces 3, which is half of 6, and this one produces 5, which is half of 10. In fact, you can do essentially any computation with a cellular automaton. Some of them have to be a little bit more complicated, like you have to have 3 states instead of 2. You can square things, take square roots. You can make logic decisions. You can do ors, ands, exclusive ors, and so on, all with cellular automata, which is something that makes them very interesting. Here's Rule 110. This is the famous Rule 110, specified in the standard way. And it's what we saw on the right-hand side on the first slide. And what I've done here is I have a set of different random initial conditions at the top, and then started the cellular automaton working. And you can see that it's producing these interesting structures that you see repeatedly. You see this structure often. You see this structure often, which turns out to be a very important one. Here's that structure with the triangles that's very important that you see in various spots here. Here's another example of Rule 110, which continues for a long time. So it starts here, here's 300, it continues to 600 to 900, and you can see these structures continuing to develop and move through time and interact with each other. And here's another 900 generations, and it continues along. Now, Rule 110 is especially interesting. This rule is especially interesting because it is capable of universal computation. This one rule, you can make a whole bunch of different cellular automata, different ones with different sets of rules, do calculations. But this one all by itself, Rule 152, is a universal computer. Now, you can't get more complicated than that. From an 8-line table that specifies the operation of this device to universal computation. So this excites Wolfram, and really is an interesting, important illustration of the general idea that he wants to promote. Well, there are lots of other types of rules in this book that I'm not going to go into. Related cellular automata, you can, as I've suggested, you can conceive of automata with more than 2 states, more than 1 dimension. He talks about 2-dimensional automata in here. They can be affected by more than their nearest neighbors. There are a lot of other simple rules that he talks about in the book. I'm not going to describe them. I just put some names down there. You probably know about Turing machines. These are a little different because these Turing machines are implemented on grids. They're very interesting. But all of this is this one vein of material that I think can be mined for utility in behavior analysis. So you say, well, I'll get to that later. Here are some applications of just the simplest 1-dimensional, 2-state, nearest neighbor cellular automaton that have been developed. I'm not going to describe them in great detail. An interesting feature about applying these things, however, is that it really takes some cleverness in order to do it, and I think that's probably not really a good thing. But the idea of a cellular automaton is really extremely general, and Wolfram likes to stay very, very general about things. So when you apply this to some actual phenomenon that you're interested in, you have to, of course, talk about the phenomena that you want to describe, and then typically what happens is you map particular features of the automaton onto your phenomena in order to get a model, like a model of traffic flow. The model of traffic flow, I forget what rule it's based on, but it shows cars that clump together, and depending on density, repeated stringing out and clumping together of cars and so on. But it's a little bit odd the way they're applied because of this kind of detailed, specific mapping. Can you do that for instrumental behavior? Is it possible to do that for instrumental behavior? Well, I didn't take this route. When I collided with this book, I took a different route. I took two routes. One was a number theory route, which I'm going to talk about against my graduate students' advice in a little bit. And another was an applied route. So I'm going to talk about those pathways that I took. But here's a pathway that one could take and that I think would be interesting to take. You take this, I think this is Rule 22, and here it's expanded so you can see all the little squares, all the little cells. How in the world could something like that apply to behavior? Well, let me tell you about Rule 30. Rule 30, if you started from a single cell, the center column, as it evolves through time, the center column turns out to be a perfectly random string of ones and zeros. In any statistical test known to man that can detect non-randomness in a series of numbers has failed to detect non-randomness in that series of numbers. And in fact, Wolfram uses the center column of Rule 30 to generate random numbers in his program Mathematica, which I presume most of us know about, which is now the industry standard kind of, I guess you'd call it the industry standard mathematics software program. So if I were to do this, I didn't do this, but if I were to do this, this is what I would do. I would start with something like this, Rule 22. I would look at a column, look at one particular column that you see down there. Each black square would be a key pack. And I would make some cumulative records. That's what I would do. And what you see here, this is only a few generations expanding. You see a slowdown in responding. This is peck, 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 and so on. You could make, if you have a column, I do this in Excel, so I have 256 columns. If you have 256 columns, and you can extend them for however long you want, I would make cumulative records out of every single one of them and just look at them. That's what I would do to start. Now, you can, with Rule 110, you can put clock pulses into the debris. Clock pulses. You could arrange a Skinner box with Rule 110. You actually could do that. So because there's interaction, maybe not in Rule 22, but because there's interaction, it's possible to look at a stream of behavior like this and if you put farther away on the initial conditions a batch of cells, it can develop as you go down and at some later time interact with the stream of behavior that you've identified, which would be something like a reinforcer, for example. Anyway, it's a really very interesting idea. It would make a great dissertation project because it's completely virgin territory, very exciting. You could do really a lot of interesting things. It could turn up something interesting. It would be a very huge but really an interesting project. You got 256 rules. You're saying, oh my God, am I going to have to look at 256 rules? Well, maybe. Wolfram spent 10 years sorting through these 256 cellular automata. I'm not saying they should have a 10-year dissertation. There are probably ways to focus that into a more reasonable period of time based on what Wolfram has already done. But do you have to sift through all this different stuff? Yeah, that's probably what you would have to do. So that's something that is interesting. Now, I want to talk a little bit about my personal odyssey through after colliding with this book. And part of that has to do with number theory. And I just want to illustrate some of the things. You get from this book a real... Wolfram did a lot of work in number theory for many years himself. And it's not something that's really familiar to us, but it's just fascinating. Here's just an example, aliquot sums. Every number has an aliquot sum. An aliquot sum is the sum of the divisors of the number, not including the number itself. So if you have 6, for example, the divisors are 1, 2, and 3. So you don't include 6 in there. Actually, the aliquot sum is the sum of the divisors, not including the number itself, minus the number itself. So for 6, you have 1, 2, and 3 are the divisors. You add them up, they equal 6. 6 minus 6 is 0. If the aliquot sum of a number is 0, the number is referred to as a perfect number. If it's greater than 0, it's referred to as an abundant number in number theory. If it's less than 0, it's referred to as a deficient number. And most numbers are deficient, in fact. A thing that has been of interest for thousands of years in number theory have been perfect numbers. How many are there, and what are their properties? These are the first 10 perfect numbers. This last one consists of about 58 digits here. That's an integer. There are 44 known perfect numbers. The largest one consists of 9 million decimal digits, a number, the quantity of which far exceeds the number of atoms in the universe. All of those 44 perfect numbers are even. A problem that has puzzled number theorists for thousands of years, we learned in Wolfram's book, is, are there any odd perfect numbers? No one has found an odd perfect number, and no one has proved that it's not possible to find a perfect number. So I bring this up just because it's really, it gives you, it's very exciting really and stimulating and gives you an appreciation for numbers. Discussions of prime numbers, which I pursued after reading this book, and I want to recommend a book to you if you're interested in this line of thing at all. Prime numbers are probably the most fascinating topic in number theory. This is the Civ of Eratosthenes. I'm not going to go into it, but it's a way of obtaining prime numbers. People are still looking for prime numbers. If you Google prime number search, you'll go to the current website where people are looking for prime numbers. It's a distributed computing project. It's like SETI. You can download number crunching software onto your PC, which will calculate. They'll give you these gigantic numbers to calculate and search to determine if they're prime. If you describe, this is the largest prime number known, 2 to the 32 millionth power minus 1. It consists of 9.8 million digits. There's a prize for the prime number that consists of 10 million digits. It's like $50,000. So I encourage graduate students to look at that. Here's the great thing about prime numbers. There's a connection between prime numbers and the natural world. This is Bernhard Riemann, one of my great heroes. He was a number theorist and mathematician. He invented analytic number theory. The zeta function you may or may not know about is an important discovery of his or creation of his. He was interested in prime numbers, in particular their distribution along the number line. So number theory deals with numbers in a way that we typically don't. When we talk about numbers, we think of them as representing quantity, which of course they do. Number theorists are interested in other properties of numbers, like the sum of their divisors, or whether or not they're prime, or what the distribution of prime numbers is along the number line. And Riemann did a lot of interesting and very important work in this area, and the relationship between prime numbers and in particular the energy states of atoms is awe-inspiring. I highly recommend this book down here by John Derbyshire called The Prime Obsession is its title. You can Google it and find it. It's about Bernhard Riemann and prime numbers and the natural world. So that's my little foray into number theory. And this is a concession to my graduate students. We don't want to be teetering on the precipice of numerology here. Although some people did. This is Paul Dirac and Arthur Eddington, Paul, a mathematical physicist, important person. Arthur Eddington, they were fascinated by this number, 10 to the 40th power, which turns out to be the ratio of a number of cosmic to atomic properties, 10 to the 40th. In fact, Dirac, this is now considered to just be a coincidence by most people. But Dirac tried to develop a whole cosmology based on this number, 10 to the 40th. So we don't want to go over the precipice in talking about number theory, and so you have somebody to pull you back if you go too far. And 42, you know what 42 is? Okay, everybody knows what 42 is. That's probably over the precipice. Although notice, it is not far from the exponent on that 10. Okay. So, another feature of my personal odyssey after collision with this book was an attempt at an application to behavior along a pathway that's a little bit different. It was an attempt to apply the general thesis of the book, that simple rules can produce complicated behavior, and then, as it is typical of these applications, you have to go back to your discipline and see what's there. And there's a lot of talk, as we know, about selectionism in behavior analysis, dating back to Skinner and also John Donahoe and also Charlie Catania and others besides, Sigrid Glenn and others besides. And these are simple rules. The Darwinian rules of reproduction and selection, reproduction, and mutation are really pretty simple, at least conceptually. In the abstract, they're pretty simple. Implementing them in actually the actual physical implementation could be complicated, but the rules themselves are pretty simple. So I thought, well, if you couldn't you actually implement rules like this and see if, emerging from the operation of these rules, you could get features of behavior that were like the behavior of live organisms? And so that's what I decided to do. I decided to try to implement this. In order to implement something like this, you've got to represent behavior somehow. And here's how I represented behaviors. I said each behavior was an integer. And each integer had a base 2 representation, a bit string that represented it. That's my basic representation of behaviors. And you'll see that there's a reason for this right here. If you have this representing behaviors and you want to talk about the behaviors evolving, I mean, this is a very appealing idea, that behavior evolves in response to selection pressure from the environment in the form of reinforcement. But if you want to actually implement this and you're representing behaviors like this, well, you've got to have a population. There's got to be a population that evolves. So let's consider this as a population of potential behaviors. These aren't actual behaviors, but potential behaviors. And this is a relative frequency distribution of potential behaviors in a population extending along the integer values from 0 to 1023. I can divide this interval range however I like, and I've divided it into 2 small ranges here and 2 larger ones over here. You can think of that as like a concurrent schedule, so that the potential behaviors that fall in here are potential left keypecks. The potential behaviors that fall in here are potential right keypecks. This is potential something else, and this is potential something else. So I have a set of potential behaviors that can evolve. So in order to make all this work, you have to have from this population of behaviors a behavioral emission that you can then record. So you've got a virtual organism. It's got these potential behaviors. How do you determine what behavior comes out, is emitted? Well, do it as simply as possible. Let the relative frequency of the behaviors in each class that you have partitioned the number line into, let the relative frequency of the behaviors be the probability that you're going to get a behavior from that class at that moment. So in this case, you're not likely to get any keypecks. You're much more likely to get these other kind of extraneous behaviors here. So that's the emission rule. Every time I have a new population, I'll emit a behavior based on that rule. These are the 3 Darwinian rules. Here's the selection rule. What the selection rule says is that, let's say that this target behavior on the right key was reinforced. Well, if it was reinforced, I have to reproduce and get another generation in this scheme. I need another generation, like I have another cell in the line in the cellular automata that keep going down. I've got to have a new generation each time tick from which a behavior is emitted. So how am I going to? So I need parent behaviors to reproduce. I'm going to have the parent behaviors reproduce. How am I going to pick them? Well, if a behavior was reinforced, what I'm going to do is, by a simple rule that I won't explain right now, I'm going to tend to pick parent behaviors that are close to the behavior that produced the reinforcement. That's selection. So these behaviors way out here are not likely to get picked to reproduce. These behaviors are more likely to get picked. If there's no reinforcement, then I'm going to select behaviors at random. So I've got a bunch of parents, and then they're going to reproduce. This is just crossover recombination. These are like digital chromosomes here. I can slice them, simple digital chromosomes. I can slice them, in one spot and do crossover recombination and make that be the child. What I've illustrated here is a more complicated version, is endpoint crossover. You can have many points of crossover here. But basically, that's how you can produce a child behavior. And I'll tell you and ask you to accept on faith for now that when you do reproduction this way, the children resemble their parents, which is, of course, essential. If you have 2 parents that are like the target behavior, they're going to tend to produce an offspring that is like the target behavior also. So that's the reproduction rule. And then I have a mutation rule. So this is how I get a whole new population for the next time tick. And then I add a little mutation. I'll just pick a behavior or 2 or by some percentage, and I'll just flip a bit at random. That's mutation. So that's the entire table set by which this virtual organism operates. So this is comparable to the Wolfram 8 neighbor rule table. This is just the table that shows how to apply the rules to get behavior emitted from generation to generation. So you see what happens is every moment some behavior is emitted. And these these processes of selection, reproduction, and mutation alter the population of potential behaviors. And basically what tends to happen is that behaviors that are behaviors reinforcement tends to concentrate the behaviors in the target classes, and non-reinforcement and mutation tend to make the behaviors distribute among all the classes of behavior. That's what happens. And then you reach an equilibrium after a while, a dynamic equilibrium, where you have a fairly steady response rate. An interesting thing about this application of the simple rules producing complex phenomena is that it produces behavior that can be studied just like the behavior of a live organism. You can put this organism on anything that you can put a live organism on. Here's an example of some results to look at the emergent properties. This is 500 generations of acquisition followed by 500 generations of extinction. The pen resets at the start of acquisition. These are 5 different runs. You can think of it as 5 different organisms operating by those Darwinian rules. And what you see is that you get a fairly, this is an RI-25 schedule, by the way, a random interval 25 schedule. I didn't put the reinforcers in here, but you see a fairly constant rate of responding. A lot of the runs look alike, but some look different. This one started out fast and then slowed down. This one's really sluggish down here. And then extinction started, and you get a little bit of responding, and then it falls away. Some fall away a little bit more slowly. So there's a lot of variability from organism to organism, just as we see in our live organisms. And here is your standard rat that doesn't behave in your experiment. This rat's put on extinction and won't stop. Eventually he's going to stop, but he hasn't stopped so far. But all of them are operating by the same set of rules. Here's another example of many, many more generations, of 20,000 generations or so on an RI-10, an RI-40, and an RI-70. Constant rates of responding you see, as you would expect. A few little perturbations here, little pauses and irregularities here and there. And also you see that the rate of responding declines as the schedule becomes leaner, as you would expect. Also, this is just an example of what happens on a concurrent schedule, and I'll just tell you what it shows. It shows alternating bouts of responding on each alternative. We have not published any data on concurrent schedules, but well, I'll get to that in a minute. But here's what happens on them. Here you're on alternative 2, and you see you're responding on alternative 2, but not on alternative 1. These timelines are lined up. Here, so you're responding on alternative 2, then you stop, and you've switched over to alternative 1, then you stop, and you've switched over to alternative 2. So you get sustained bouts of responding on the 2 keys. Again, there's no difference. Everything, the operation of this device is completely described by that slide that I had up there before. Interestingly, not only are these detailed properties of behavior emergent from these simple rules, but also time averaged properties of behavior emerge from these simple rules. And this is an example of single random interval schedules and an equilibrium outcome that's consistent with Herrnstein hyperbola. This is concurrent random interval schedules, and here's an outcome consistent with power function matching. And these exponents tend to be about 0.8 for some miraculous reason. The exponent turns out to be 0.8. This is a distribution of a lot of different experiments of the exponent, and it has a very strong mode at 0.8. There's an exponent of 1.0. So I just have put this on here to illustrate this kind of application of the general thesis of the Wolfram book. We're going to have a symposium on this on Monday, if you're interested, at 3:30 over in the other hotel in Barbershop, where I'll be able to explain a lot of this in more detail. All the concurrent schedule data is new. We've published this, but we have not published the concurrent schedule data. So that's going to be interesting to talk about on Monday. Well, okay. Have we seen stuff like this before in behavior analysis? Sure we have. We've seen this kind of complexity approach. People have talked about it today. Shimp was probably the first. Momentary maximizing is the same idea, where the simple rules are repeatedly applied to produce large-scale outcomes. Selectionist neural networks, John Donahoe has studied those. The reflex reserve, Charlie Catania has been interested in that, which is the same kind of idea. There are simple rules and complex phenomena. At our symposium on Monday, we're going to talk about this also. And then selection by consequences. And this is really very interesting. This idea of neuronal group selection, or neural Darwinism, by Gerald Edelman, who's a Nobel Prize winner for his work in immunology. You might know that name from there. Dovetails in an interesting way. He's a proponent of the same idea, this complexity thing. Dovetails in an interesting way with this selection by consequences, more abstract account. So the final take-home message is that, yes, the simple rules approach that Wolfram champions in this book is worth pursuing in behavior analysis, it seems to me. And it would repay you to take a look at that book if you can manage to get through the prose and the repetition in it. And that's it. There are questions or discussion?
It's about 4:45, so I guess we have time for questions.
Billy?
I find this fascinating, and I've corresponded with you about it. A lot of these evolutionary models that I've seen just assume haploidy and don't bother with the father and the mother part. And I have a feeling that you don't need that. I think you can just have the mutation rule and you'll probably get all the results.
Well, it does not work, in fact. We've tried that. We have worked on that, and we haven't published anything on that, but you get, in concurrent schedules, you get very low exponents. There are certain conditions where it works, but it doesn't have the broad robustness of the case where you have actual recombination. So that's what happens in concurrent schedules, very low exponents. And in single schedules, you get not a hyperbola, but an asymptotic exponential is describing the data. So why that should be. Interestingly, Edelman's theory of neuronal group selection is based, it does not include any kind of recombination.
So that suggests that the combination there in there, the mutation and the reproduction, are actually representing rules that are important to the process.
Yes.
So I mean, even if you take away the analogy to the reproduction, what you're saying is you need some slightly more complex mutation rules.
That's right.
You need the recombination.
Yes, you do. You do, as far as we can tell. Now, I gave a talk at a evolutionary computation conference in Seattle. It was very fun to go out into these other kinds of groups and try to talk about this kind of stuff. And one of the guys said, yes, well, it's when the magic happens. Mutation is great. People who study genetic algorithms in engineering, for example. Mutation is great, but the magic happens when you've got recombination and mutation. And that does seem to be the case here. John.
No, that's fascinating. I actually thought
Oh, did you? How far did you get?
but I think I've learned more in this talk.
Oh,
And the rest are quite actually reading it. On the other hand, my biceps are
yes. It's true.
I was going to ask you if you've done any simulations of history effects, on the kind of thing I talked about this morning.
Yes.
Randy has done, and John Donahoe and so on, where if you train the animals separately with the two choices, then they fixate. Does your model do that?
I don't know, but we can try that. And that,
a simple thing to try.
yes, it would be a great thing to try. And also, Billy and Michael Davison's pulse thing, you can run them on that too, and look at how the.
Well, I think the history effects, the effects of the long-term past history, is that immediately what people say, well, this can't do that kind of thing, so it'd be good to show you.
Yeah, I'm thinking that it could, but I think what you might need is larger populations. We use 100 member populations. I think you might need bigger populations of potential behaviors that can then retain that past history for longer periods of time. Yeah.
I'm just curious. Maybe the answer is implicit or obvious in your model, but I sort of think about this sometimes. But how might you integrate or account for interval effects like fixed interval scallops or things like
Yeah, I don't know. That's going to be problematic. We're going to have to think of that down the line. I'll tell you what the next thing on the menu is for this, on the to-do list, is stimulus control. And I've got a plan that comes from my interest in artificial life and artificial intelligence, where a typical or a canonical problem is an agent traveling through a grid world to acquire resources. And how does the agent learn? Because reinforcement learning is a big topic in AI. I mean, it's huge. Adaptive behavior is like really, really important. What do? They take engineering solutions. They say, you know, what would the engineer decide? In artificial life, they say, how has evolution solved this problem? But they don't know as much as we do about that. So we can contribute a lot, I think, to artificial life. But the problem of the agent in the grid world, where an agent's in a grid and he can either go north, south, east, or west, and then he makes that move and so on, and then encounters a resource, and then how does he learn that that's a good path? Do you do expected utility that goes backwards like this? Do you do a policy search through repeated trips? That sort of thing. But I think that you can do it this way, but we're going to have to add stimulus control, which would be a good thing to add anyway. And so that's really my next thing on the list. But these other things are really very interesting and could certainly be run.
Yes, like everybody else, I find it fascinating. And I do have a problem in conceptualizing how this approach allows you to let the theory interact with an experimental program. I can see that you may have some phenomena that you know, and you try to find which rule actually can reproduce the phenomenon that you have. But of course, that's only the beginning. I mean, you formulate your hypothesis. How do you go about later on? I mean, you are going to, normally, when you change a hypothesis in your theory and then do an experiment, your hypothesis is formulated at a heuristic level. What if things are different? Here, it would seem like you would say, what if I put a 1 or a 0 in the square, in such a square, then what does it do? And I'm going to test that. So I just fail to see it. I mean, I realize it's a bit naive as a question, but I can't. I'm able to use it because I don't.
You're talking about the connection between the model and experimental data. Is that what you're talking about?
Yes.
Okay. I think this is the kind of thing, and Wolfram makes this point in an interesting way. He, by the way, has talking points now on this book. If you go to wolframscience.com, you can find talking points, because people can't understand what he's saying in the book. So he's a PDF file that summarizes like the basic points in the book. And one of them is that he's really talking about an extremely general kind of theory that he wants to describe everything. And he thinks that there are a few simple rules that describe the entire universe: the Big Bang, the development of the galaxies, life on Earth, everything. A few simple rules. That's why I say he's an extreme practitioner of this point of view. But I think the approach really is not one where you would say, how can I apply this to a specific experimental result? It's more, what are the really well-documented experimental results that we have in our discipline? What is our basic, that everybody agrees on, essentially, is true and happens, and those are the things that you would want a theory like this to reproduce. So it wouldn't be, I don't really see it as a kind of theory interacting with experimental work on a sort of day-to-day basis, where the experimental work would be, the accumulation of findings that any theory, of course, is going to have to be able to account for, but it could take many years in order to determine that a particular experimental result is worth bothering about, in a large-scale theory. So it wouldn't really be a theory like the kind you were talking about, where you take that particular set of data and look at different kinds of models. I don't see it that way anyway.
Another question?
There are so many questions that come up. I was with Alex on that one, and I wonder, how do you choose the initial conditions, and what about biases that are the outcome of a species phylogeny and things like that? Have you thought much about?
Yes, and Soli Kulebekova, she's going to talk tomorrow in our symposium about the micro properties of behavior on these schedules, and how I haven't really described all the details of the steps, but there are properties of, for example, the selection function, which is really just a linear it's a linear probability density function, but it's got a slope. And that slope is changeable, can be changed. It turns out that you can get all of these results no matter what the slope is, or if you use an exponential function, or if you use a uniform probability density function. However, some of those features may, in fact, represent different kinds of species behavior. For example, in log survivor plots, we know that if you, or even particular behaviors, in log survivor plots, it appears that if you do nose poking in rats, you get the burst pause thing. That's what Rick Shull finds. But if you do other kinds of behaviors like lever pressing or keep pecking in a pigeon, you tend to get a smoother log survivor plot. And so these features of behavior could be unique to particular species, and it may be that some of the properties of the rules that are used can match those species differences or even behavioral differences. But there are no initial conditions. You've got a virtual organism and it operates by the same rules, and you stick it in a Skinner box.
So I kept thinking about the guy who claimed that if you put so many monkeys in a room that they would eventually type out, all the great literature of the world. And so it raised the problem or the issue for me, which was I'm not sure you have interpretations. So we have patterns. What we've got are patterns. So the question is, what are the rules for seeing, for translating those patterns that you see into phenomena that you're interested in? You've got multiple ways to map, and so sometimes it'll be on the way it visually does this, or another way. So I'm just wondering if there are a set of rules.
Okay.
How big a projection?
All right, you're talking about the cellular starting with the cellular automata?
I'm talking about, yes, doing
Yeah.
cellular
Yeah.
automaton, then identifying operant effects visually, that.
Yeah. The fact is there is no way to decide. Here's what Wolfram would say. He would say, I think, that you just go looking and you're going to find a bunch of nothing, and then you're going to find your answer. He claims that when he has tried to set up rules to produce a particular outcome, he's much less successful than when he picks the simplest kind of thing he can think about. And that then describes the outcome. That's his general view. But no, there are no rules for translating those particular structures into phenomena. You have infinite degrees of freedom there. So that's not good. That's not a good thing. But if in fact you have 100 ways to map and 99 of them do nothing, but only one does, then you found it. You found the one that works just by searching.
Right, but then you should be able to follow up. If it works in a particular way,
yes.
In this instant, you would like to have the next schedule. Or the next
you absolutely would. Absolutely.
It reminds me of Rorschach's a little bit.
Yes, it does. It does indeed.
And there's not but it's not quite the same.
No, that's why I'm saying the application part is a little bit, very special, and you have to be clever, maybe there are too many degrees of freedom. There could be. I'm uncomfortable with that as well. That maybe if you don't like one thing, you try another. If you don't like one thing, you try this. You have 5 different ways to have 5 different simple schedules. Well, that's not going to be a good application.
Right.
I agree.
Yeah. No, I think it is interesting, but I do have that problem. I'm not quite sure.
As I mentioned in your introduction, this obviously has a great deal of implications about the nature of modeling itself. And these sorts of approaches, for one thing, unlike, let's say, traditional differential equation modeling, which are based upon particular kinds of principles, chemical, physical, whatever, there's no essential principle here. And so you're looking for a set of rules that will generate certain kinds of features that you find in nature. without the implication that somehow nature is actually following those rules. And then the other question about uniqueness. There has to be a zillion different ways of carrying out these procedures that may yield up exactly the same outcome, which is just another way of saying these rules don't reside in nature in any way. They have to do with your computational procedures in generating these phenomena. And of course, you would hope that it would also be able to predict phenomena you didn't even know about yet, which is not clear how that's going to work in this context.
Yeah, Wolfram has discussed all of these things. I'm not completely sure I understand what he's talking about, but indeed it is the case that Wolfram will agree that there could be many different sets of rules that produce the same outcome. He doesn't care about that. I'm not sure why he doesn't care about that. But that's part of, I think, the new kind of science, to not care about that. So you say, well, does that inhere in nature somehow? I'm not sure that that's a question that would be relevant to what Wolfram sees.
In any case, but it is the sort of tradition in which we've looked at
it is.
nature.
It is, and I'm more comfortable with that tradition. I will say, interestingly, that the evolution thing I always thought of it as being so abstract until I stumbled across the all of Edelman's work, which is a physical instantiation of that very thing. It's a very unusual kind of neuroscience thing. He doesn't want to talk about anatomical structures. He says the functional organisms of the functional organs of the brain are groups of neurons that subserve adaptive behavior, and those groups are selected by interaction with the environment. That's the Edelman view. He basically builds what he calls brain-based devices. Look up Edelman Science November. Last November, there was an interesting article in Science where he has developed a little robot that is animated by the theory of neuronal group selection that does elementary operant approach and avoidance behavior, and he talks about it that way. It's really interesting. Okay.